When gas is produced with oil, the pressure of that gas after separation is often not great enough to enable it to enter the gas transmission line. And high-pressure gas is also needed in some fields for gas lift and injection purposes. So, a method must be provided to increase the pressure of the natural gas to meet these requirements. And here is where reciprocating compressors play their role. This is the first section of a three-section module dealing with reciprocating compressor principles. The simplest and probably most familiar reciprocating compressor is a bicycle pump, just like this one, used for inflating footballs, basketballs, tires, etc. Now, by reciprocating, we mean that the piston moves back and forth in a cylinder. Air pressure is increased by the thrust of a piston within a confining cylinder. Now, the most common field compressor is also a reciprocating compressor, like our bicycle pump here. Gas pressure in this compressor is increased by the thrust of a piston within a confining cylinder. Reciprocating compressors are positive displacement compressors. Positive displacement means that a fixed volume of gas or air is discharged and replaced by the piston. That is, the thrust of the piston raises the pressure of the gas, and the gas is released, with the piston replacing the empty space. Movement of the piston from one end of the cylinder to the other end is the stroke. A forward stroke is movement of the piston away from the drive end of the compressor. Movement of the piston toward the drive end of the compressor is the backstroke. The full stroke is the movement of the piston from one end of the cylinder to the other end and back to its original position. A compressor which compresses gas on only one side of the piston is commonly called single acting. Gas is drawn into the cylinder through the suction valve during the backstroke. On the forward stroke, the gas is compressed and discharged through the discharge valve. Now, the double-acting compressor compresses gas during both the forward and back strokes. On the forward stroke, gas is drawn into the cylinder through the suction valve on the drive end. At the same time, gas is being compressed and discharged away from the drive end on the opposite side of the piston. On the back stroke, the process is reversed. Gas is drawn into the cylinder away from the drive, and gas is discharged on the drive end. Now, a typical reciprocating compressor consists of compression unit, drive unit, and the distance piece. The compression unit compresses the gas. The drive unit supplies the power, and the distance piece is the housing which joins the two units. Because the reciprocating compressor has numerous moving parts, lubrication of the compression unit and the drive unit is crucial to smooth compressor operation. In addition, the temperature increases within the compressor caused by the friction of the moving parts and from compressed gas. In order to remove this heat, cooling systems are also required. Well, now that we have a general concept of how a compressor operates, let's break it down into parts and look at each in more detail. Starting with the compression unit. The end of the compression unit, farthest from the drive unit, is the head end. That end closest to the drive unit is the crank end. Inside the cylinder is a double-acting piston. Surrounding the cylinder, inside the compression unit housing, are gas jackets. Typically, the jacket is divided into top and bottom jackets. The top jacket is the suction gas jacket, which supplies gas to the cylinder. The discharge gas jacket on the bottom receives the compressed gas. A suction line connects the compressor to the gas source. Gas is drawn into the cylinder from the suction gas jacket through the suction valves. The compressed gas is discharged through the discharge valves into the discharge gas jacket. The discharge line connects this compression unit to the next unit or pipeline. Once a reciprocating compressor is placed into operation, a continuous flow of gas is established. On the piston backstroke, cylinder crank end pressure is increased. When this pressure exceeds pressure in the discharge gas jacket, the crank end discharge valve opens. Gas is then discharged from the crank end of the cylinder. At the same time the movement of the piston in its backstroke increases pressure in the crank end, pressure in the head end is reduced. When this pressure is less than the suction gas jacket pressure, the head end suction valve opens. Gas is then drawn into the cylinder. On the forward stroke, the gas in the head end is compressed and discharged from the head end of the cylinder while gas is being drawn into the crank end portion of the cylinder. With the backstroke, the process begins again. Various types of valves are used in compressors. A typical valve for a heavy-duty reciprocating compressor, such as this, is the plate valve. In a plate valve, the part which closes against the valve seat is a flat metal plate. These plates are held against the seat by a set of springs. Before we discuss the operation of valves, both suction and discharge, there's a very important point that needs to be understood. Both suction and discharge valves are identical pieces of equipment. Their function as suction or discharge valves depends solely on their placement within the cylinder. A suction valve opens whenever the gas pressure inside the cylinder is less than the suction gas jacket gas pressure. When the pressure relationship is reversed, the springs close the valve. To open a discharge valve, the gas pressure inside the cylinder must exceed the gas pressure inside the discharge gas jacket. Again, when the pressure relationship reverses, the springs close the valve. Well, this concludes our first section, dealing with the principles of operation and components of reciprocating compressors. Take a moment to review your manual. View this tape again if necessary, and then continue in your manual by filling in the blanks and labeling the diagrams in Section 1. Our next section will cover in a little more detail the operation of the compression unit. See you then. In the first section, we viewed the basic components and operation of a complete compressor. Now we'll look at the parts of the compression unit in more detail. We'll see how cooling is accomplished, how the unit is lubricated, and how its capacity for compression can be altered using the clearance pocket and valve unloaders. This is the second section of a three-section module dealing with reciprocating compressor principles. As we noted in the first section, compressing gas increases its temperature. Because of this, a compressor must have a mechanism to remove some of the heat generated by the compression process. For a small reciprocating compressor, such as an air compressor, fins surround the cylinder. Now these help to remove the heat by increasing the radiating surface, which provides air cooling. However, for most large, heavy-duty reciprocating compressors, air cooling cannot remove enough heat. Therefore, the cylinder and head of these larger units are jacketed to allow for circulation of a cooling liquid. Like a car radiator, this liquid is usually water. In fact, to assist in the heat exchange process, the water also circulates through an aerial radiator, like the one seen here, which further removes the heat. Now let's talk about the cylinder. The ends of the cylinder are equipped with removable heads. These heads, a head-end head and a crank-end head, may also contain cooling jackets. Within the crank-end head is a set of metallic packing rings. These rings prevent gas leakage around the piston rod. As the piston reciprocates within the cylinder, friction caused by that movement will create wear within the cylinder. Because of this, most cylinders are fitted with a liner, and pistons are also fitted with rings. Now, by replacing only liner and rings, a cylinder may be repeatedly repaired without having to replace the entire compression unit. In the cylinder wall is a lubrication inlet. Lubricant or oil forced through the inlet is spread over the length of the cylinder by the piston rings during the stroke. At the same time, lubricant is also force-fed to the packing on the piston rod. For some reciprocating compressors, the compression unit and drive unit lubricants must be kept separate. Wiper or scraper rings perform this function. Scraper rings located on the crank end of the cylinder remove compression unit lubricants from the piston rod. The wiper rings on the crank end of the distant piece remove the drive unit lubricants from the piston rod. Both waste lubricants then collect in the distance piece and drain to a sump line. As we saw in the first section, natural gas is compressed by the reciprocating motion of the piston. However, not all the compressed gas is released at the end of the stroke. Some of the gas is left in the cylinder. This is the result of a clearance space, which is made up of the spaces in valve recesses, plus the space which exists between the piston and cylinder end at the finish of a stroke. On a reciprocating compressor, a clearance pocket can be installed on the head end. A clearance pocket is termed fixed volume if the valve of the pocket can only be either open or closed. However, the clearance pocket may also be a variable volume type, which allows the operator, using the hand wheel, to adjust the volume of the clearance space. Using the clearance pocket to change the clearance space, an operator can control the capacity of the compressor. This can be accomplished either manually or automatically. Manual operation is accomplished using a hand wheel. Under normal compressor operation, the suction and discharge valves open and close relative to the piston position. However, the valves may also be equipped with devices called unloaders. An unloader is used to alter the load on one end of the piston. By unloading or opening the valve, we decrease the capacity of the compressor. Like a clearance pocket, unloaders may be operated either manually, using hand wheels, or automatically, using a device called a pilot, which uses suction or discharge pressure. In summary, let's look at what we've seen in this section. You've seen how heat builds up as a result of gas compression, and that either air or water cooling must be employed to maintain smooth operation of the compressor. As a result of friction, the compressor must also be kept properly lubricated. You've also seen how a clearance pocket may be utilized to vary the volume of the clearance space and therefore the capacity of the compressor, and how, by using unloaders, the capacity of a compressor may be decreased. Well, again, review the information found in your manual. Look at the tape again, if necessary, and fill in the blanks and label the diagrams. Our final section in this module will cover the drive unit and how gas pressure can be increased using multi-staging. In Section 2, you were introduced to the compression unit and how it operated. In this section, we will cover the drive unit. You'll see how the crank end transfers power to the compression unit, how the compression unit and power source can be integrated, and how gas pressure can be increased using multi-staging. This is the third section of a three-section module dealing with reciprocating compressor principles. The drive unit of the compressor supplies the power for compression. Rotary motion from the power source is converted to reciprocating motion by the crankshaft, connecting rod, and crosshead. Let's take a moment and look a little closer at how each of these parts functions. The crosshead joins the connecting rod and piston rod. Passing through the distance piece, the piston rod drives the piston. The crosshead allows the piston rod to move only laterally, yet allows the connecting rod to have rotary motion. A lock nut secures the piston rod to the crosshead. The connecting rod is attached to the crosshead with the crosshead pin. The crosshead travels horizontally and must have limited vertical variation. Its confinement is maintained by the flat or circularly bored crosshead guides. Inside the guides, the crosshead shoes maintain the vertical position of the crosshead. While the shoes are replaceable and adjustable, shims on both of the shoes provide additional adjustment. Both ends of the connecting rod are equipped with heavy-duty sleeve bearings. These bearings are adjusted using the adjusting wedge and adjusting bolts. The sleeve bearings may be made of babbitt, bronze, or aluminum. Inside the sleeve bearings, the crosshead pin and crank pin are separated from the bearings by a film of oil. This is crankcase oil supplied under pressure through holes in the bearing surface. The power to operate the compression unit is usually supplied by either electric motors or engines. The most typical, however, are combustion-type engines. In these, power pistons are connected by connecting rods to the crankshaft. In addition, the crosshead is connected to the crankshaft by a connecting rod. Thus, rotation caused by the power pistons is translated by the crankshaft, connecting rod, and crosshead into reciprocating motion, which powers the compression unit. Now, just as lubrication promotes smooth compression unit operation, lubrication of the drive unit is equally important. However, lubrication of the drive unit will be covered in a later module. Often a compressor has more than one compression unit on the same frame. In these arrangements, each compressor piston is powered through the same crankshaft. One example of a shared crankshaft is a balance-opposed compressor, like this one. The cranks are arranged so that the motion of one piston is balanced by the motion of the opposite piston. Balance-opposed compressors are often externally driven. The compressor crankshaft is coupled to an engine or electric motor. Others may be engine or motor driven through a V-belt drive or motor, or turbine driven through speed-reducing gears. When the compression unit and power source are on the same frame, the term applied is integral unit. In this arrangement, the compression unit and power source share the same crankshaft. The compressor cylinders are usually horizontal. The power cylinders, on the other hand, are either vertical or at a V angle to the horizontal. In certain instances, gas must be compressed from a low pressure to a high pressure to meet sales requirements or field applications. This increased pressure is accomplished through stages of compression. But due to the amount of power required, it's not feasible to raise the pressure of the gas from low pressure to high pressure in just one step. Because of this, we use what's called multistaging. Each stage or cylinder increases the pressure until a desired range is reached. A compressor which does this stage compression is called a multistage unit. Now, depending on the pressure requirements, 2 or more single-stage units may be assembled in one housing for improved efficiency and, of course, reduced costs. Because of the increased amount of work being performed by multistage units, additional cooling is required. Not only must the cylinders be cooled, but the gas must also be cooled between stages using devices called intercoolers. To aid in this heat transfer, radiators or aerial coolers are also an important part of the cooling system. In this section, you've seen the role the drive unit plays in operating a reciprocating compressor. You've seen how the crank end transfers power to the compression unit and how the compression unit and power source can be integrated. You've also learned how natural gas is compressed to higher pressures through multistaging. In our module on reciprocating compressor principles, you've learned the basic concepts and operation of a reciprocating compressor. You've seen how and why gas compression is important. You've also learned the basic parts of a compressor and how they operate together. Due to friction and the process of compression, you've also learned that proper cooling and lubrication is vital to efficient compressor operation. And finally, you've seen the different sources of power for a compressor and how this power is transferred to the compression unit. All right, take a minute now to review Section 3 on the drive unit in your manual. If you have any further questions, don't hesitate to ask your instructor. He is there to help you. Remember, natural gas is a vital source of energy. The proper compression and transmission of that gas relies on the safe operation and maintenance of the reciprocating compressors. And they rely on your skill and on you.